Hello, welcome to lecture 5. So here we will continue the earlier derivation that we were doing regarding the stresses in a fluid and how it's related to the how it could be put into the momentum equation. So the hydrostatic part of the this is the last slide that we stop where we stop. The hydrostatic part of the stress is isotropic, so it must be of the form of something like this, where P is the thermodynamic pressure and delta is the isotropic tensor. The Kronecker delta is the isotropic tensor of is the only isotropic tensor of second order. Negative sign is because the pressure is by definition compressive, and by convention tensile forces are taken to be regarded to be positive. So we have tau ij is minus P delta ij plus lambda del uk del xk delta ij plus mu del so this is the this is where we have used the fact that tau ij can be decomposed into the hydrostatic and the deviatoric parts, and this is the general constitutive relation. So this is the general constitutive relation of a homogeneous isotropic Newtonian fluid. Newtonian fluid. So it's important that it's a Newtonian fluid. So the shear stress is linearly proportional to the rate of strain or the velocity gradient. Now, plugging tau ij in the momentum equation, we have rho dui dt is equal to minus del p del xi plus del xj mu del ui del xj plus del xi lambda plus mu del uk del xk plus rho gi. Okay, so this equation is valid for both compressible and incompressible force. Valid for both compressible and incompressible force. Now, we'll use a hypothesis called the Stokes hypothesis. We replace lambda in the above equation by minus 2/3 of the 2/3 mu, and we get rho dui dt equal to minus del p del xi plus del xj mu del ui del xj plus del xi mu by 3 del uk del xk plus rho gi. Okay, so this is an important equation, and it's a very interesting partial differential equation, and this is called the Navier-Stokes equations. It's the plural form because there are three components here, and this is named after two scientists, engineers, Claude Louis Navier and George Gabriel Stokes. Navier was a French civil engineer, and Stokes was an Irish mathematician and a physicist who made contributions to giving rise to this form, this that uh, governs the fluid flow, that gives us the evolution of the velocity because of the various forces acting on the fluid elements. For an incompressible flow, which is the system of our concern actually, I mean, this is the incompressible limit we'll be working on. For an incompressible flow, for an incompressible flow, we get rid of the term that gives us volumetric expansion, and we have this form of the Navier-Stokes equation for an incompressible flow. So this Navier-Stokes equations, in most cases, incompressible limit is valid, because the flow speeds are, in most cases that we'll encounter here, are slow enough so that the pressure differences generated, the pressure field generated are not strong enough to create appreciable changes in density. So we will be working in this limit. So for an incompressible flow, this is the form of the momentum equation, and the conservation of momentum equation itself is called the Navier-Stokes equation. So once we have this form, now if you recall that I mentioned that this is the form that we are deriving for an inertial frame of reference. Okay, so this is very important because next we will be moving so this is valid for inertial frame of references. So Newton's laws are valid exactly in this form, whereas the frames of references that we'll be using that uh, we'll be using for measurements of geophysical flows are frames of references which are attached to earth, that is, they are moving with earth. Okay, so these are non-inertial frames of reference, and we will see how the equations are modified with the because of this frames of reference being non-inertial. So but let us do some basic studies first. So we'll see uh, uh, how our momentum equation is modified because our frame itself is rotating. But we'll see why this is rotating. So first of all, the laws of motion are valid in the inertial frames of reference, and that is also one definition of inertial frame, where laws of motion, that is as in the Newton's second law, is valid. So those are inertial frames of references. However, this is impossible to find an exactly inertial frame of reference. So this is just a note for you. um, it is not possible to find a frame of reference that is exactly inertial, because whatever you consider, um, whichever frame you consider attached to any body might be always moving in certain direction, or it's rotating, or it's having an accelerated motion. So however, certain frames of references can be assumed to be inertial for the purposes, but it depends on the purpose. For example, if you're doing a lab scale flow, then something can be taken to be an inertial frame, whereas if you're taking a geophysical flow, though that same frame may not be inertial frame. So just give us, I mean, we'll take a minute or two to get to the frames of references which are of our interest in this, and which we routinely used. So in frame attached to the Earth's surface, so frame attached to Earth and rotating with it at a constant angular velocity, assuming that the Earth's its rotation is constant. So the frame attached to the Earth and rotating with it can be approximated to be inertial when scales of motion motions are not large enough to be affected by the rotation. When scales of motion to be affected by rotation. So for example, flows in a channel or a pipe in a lab. So in a lab scale, let's say we have a 1 meter length pipe, 1 meter, 2 meter length channel, and there is a flow which is going from one end to the other. We have a pump which is pushing the fluid from one end to the other. This flow is not affected by the Earth's rotation, and the effect is very minimal because the dimension of the flow is very less as compared to the radius of the Earth. However, let's consider certain flows of hundreds and thousands of kilometers. For example, flows in the atmosphere, a jet stream. That is, I showed you. I gave you some multiple examples of certain phenomena which are in the one of the previous classes. And these could be atmospheric and oceanic flows, could be of hundreds of kilometers. These are much bigger than a lab scale meter scale flow, and hence these are affected by Earth's rotation. However, for these kind of systems, for example, flow in a pipe, flow in a channel, flow in a flow around a turbine blade, or a bird flying through the, let's say there's a bird which is flying and you want to understand the flow dynamics around the bird. For all of these, a frame attached to Earth can be approximated to be an inertial frame. And what is a frame attached to Earth is something which you are standing in. Currently, if you want to do measurements in a pipe flow, let's say there's fluid going in, fluid coming out, you want to do a measurement. Let's say you have a camera here, there's a person standing here, and you are doing measurements, you're looking at it, and you are fixed to the Earth and you are rotating along with Earth, and this is you are assuming it to be an inertial frame of reference because your scales of motion are small here compared to the radius of the Earth. So for example, you're looking at the flow around the turbine blade. You're fixing your lab frame as your inertial frame, and you're assuming that the rotation of the Earth is not being affected because the scales of motion are small. So this is so we are approximating this frame that we are moving along with Earth to be approximately an inertial frame of reference. However, as scales of motion become large, As scales of motion become large, the frames of reference, the above frame, or the earth fixed frame of reference, is no longer an inertial frame, is no longer an inertial frame. For such motions, for what kind of motions? Large motions, for example, atmospheric flows, hurricanes, or oceanic waves. For such motions, a frame attached to the Earth's center with its orientation fixed relative to distant stars. Okay. Is taken distant stars is taken as an inertial frame. Now there is a difference between a frame which is attached to Earth and frame which is attached to the center of the Earth. So just a schematic. So if you have, so this is the Earth and a frame which is attached to the Earth's center and its orientation fixed relative to distant stars. So there are stars at a distance. These stars are assumed to be stationary because their motion as viewed from the Earth is very tiny. So they are approximated as stationary, whereas even they are also moving. So that is the reason I told you that it's impossible to find an exactly inertial frame. But for this case, a frame which is fixed to the center of the Earth, with its orientation now fixed relative to these stars, so we just fix it and keep it like this, is an inertial frame of reference for for large scales of motion, whereas for small scales of motion, a frame of reference which is attached to the rotating Earth can be taken as an inertial frame. So this red one is the frame of reference that I was talking about in the previous slide. Here, this is the frame of reference, but now I am talking about this frame of reference which is given by this yellow frame of reference that I have drawn. So this is the second frame of reference that I'm talking about. So this is a frame which can be considered inertial for large scales of motion, motions which have large scales. So our measurements of geophysical flows are however based on moving frames of references. So our measurements of geophysical flows are based on frames of references moving with Earth. Now why do we do this? Because if we measure our flows with respect to a fixed frame of reference, that is the yellow frame, which is, let's name it as capital X, Y, and Z, or this is so this capital X, Y, and Z, we'll always be having moving boundaries. So the Earth is always rotating, so we'll always have to take care of the moving boundaries. So we'll always have to keep subtracting the ambient rotation. So we don't do that. So for our purpose for our convenience, it is it is useful for us to measure something which is moving along with the earth. For example, we are rotating with the earth, but we are still measuring something which is moving in the ocean or the atmosphere using our frames of references. For example, we have a temperature sensor in our hand, we have a velocity sensor in our hand, we are measuring the geophysical flows with that frames of reference, with from that frame of reference. And it is more convenient for us to manipulate the equations of motion rather than having to deal with moving boundaries altogether for always and having to subtract the ambient rotation all the time. So we measure from this frame of reference, which is given by red. So we are still measuring our geophysical flows in this using this red frame of reference, but we are considering this yellow frame of reference as the inertial frame. So we are measuring in this rotating frame of reference, and hence we need to modify our equations of motion. This is because the second law of motion, the conservation of momentum, holds true for an inertial frame of reference. But now, because we are measuring from a non-inertial frame of reference, we need to see how we can transform our equations of motion so that they are also valid there. So let's start with a 2D coordinate system. Let's start with a 2D coordinate system. So we have an inertial frame of reference, and then we have a non-inertial frame of reference. So for the sake of simplicity, I'm just using the same so I'm just doing it on a 2-dimensional system, whereas the earth is 3-dimensional, but it does not matter. So we will extend our derivation to the 3rd dimension, and we'll see that we can easily derive the modifications to the equations of motion. And now I'm also assuming that both of them have the same origin. Okay, so this is also not an assumption that will break any certain break any physics. It is just for a simplification. So let's say this is the origin, and we have two frames of references, capital X and Y. So capital X and Y is the inertial frame of reference, which is stationary, and small xy is the a rotating frame of reference. Now rotating frames of references are non-inertial frames of references, and this is because the earth is rotating and we are rotating with earth, and hence we are trying to derive how the equations of motion will change when there is when the frame of reference itself is rotating. Now there is a certain point, there's a certain point R, which is there's a certain point which is at a distance R from the origin, and this distance is Y, this is X in the small coordinate, the rotating coordinate system, and this distance is capital Y, and this distance is capital X in the fixed frame of reference. And this frame is rotating at an angular velocity omega. So omega is the angular velocity of the frame of XY frame with respect to capital XY. And the distance theta, that is the angle theta, or whatever the angle that small x has made with capital X, is omega t in time t. This is also the same angle small y has made with capital Y. So a vector R denotes a position, and in the code when you expand this position in this point, whatever point is there at a distance R in the small xy coordinate system, this distance is y and this distance is x, and whereas it's the components of the same vector in the capital X and Y coordinate system is capital Y and capital X. So frame XY is fixed, and small xy is rotating at angular velocity omega. So this is a vector. Angular velocity is a vector. So now the position vector, and this is from geometrical from geometry, you'll find that this is, and this is for you to verify, and this is not difficult to verify. This is just that just look at the components of the projected along different axes, and you will find that this transformation rules this transformation rule apply for the position vector. So this is the position vector. So this is the position, or the components of the position vector. Components of the position vector are. So now the unit vectors in each direction, in each coordinate system. So unit vectors. So small I cap is the unit vector in the small x xy frame in the x direction. So here this is the I cap, this is the j cap, this is a unit vector, and here let's mark them as capital J and mark this as capital I cap. Okay, so capital I cap, capital J cap for the fixed frame of reference, and small I cap and small j cap on, in the rotating frames of reference. So this one from the same geometric arguments, we can relate both of these. Capital I cap is I cap cos omega t minus small j cap sin omega t. So omega t is the angle that these xyz is small xy is making with capital xy. So these are the forms of the relationship between the unit vectors in the fixed frame of reference and the moving frame of reference. Hence, so dx by dt is equal to d capital X by dt. This is small x cos omega t plus dy by dt sin omega t minus omega x sin omega t plus omega capital Y cos omega t, and d small y by dt is equal to minus d capital X dt plus d capital Y dt cos omega t minus omega capital X cos omega t minus omega capital Y sin omega t. Now this one from previous relationships. This is equal to omega y and this is equal to minus omega x. So now the relative velocity, I mean the small u, which is the relative velocity, is dx dt I cap plus dy dt j cap, which is u I cap plus v j cap. This is simple. This is the velocity that is measured in the rotating frame of reference or a moving frame of reference. This capital U, which is the absolute velocity, d capital X by dt I cap plus d capital Y by dt j cap. So this is the absolute velocity in the fixed frame of reference. Okay, so now representing u in terms of rotating unit vectors, u can be expressed as dx dt cos omega t plus dy dt sin omega t I cap plus minus dx dt sin omega t plus dy dt cos omega t j cap. So this is u I cap plus v j cap. So this is the u vector. Okay, so this is the u vector and this is equal to the in terms of the rotating unit vectors, this is how we can represent this. So dx by dt dy by dt are the components of the absolute velocity u in the inertial frame, that is the fixed frame, while u and v are the components of the same vector in the rotating frame. Okay, so now similarly dx by dt and dy by dt is the rate of change of coordinates with respect to the moving frame or the rotating frame. So let's write rotating frame. So using expressions of small x, small y, dx by dt and dy by dt, in this equation we get u equal to u minus gamma y capital V equal to V plus omega x, sorry, not gamma, omega y, and then omega x. So the absolute velocity is the relative velocity. So the absolute velocity is the relative velocity plus the extra term due to the rotation of the reference frame. These are the extra terms that are being generated here because the frame of reference here, in this case, this light blue small xy frame is rotating. So anything expressed in this, when it is transformed to the absolute frame, will have some transformation, and we will see how we can now develop the same relationship for accelerations in a rotating frame and accelerations in an inertial frame, and we'll see how new terms arise in the momentum equation.